Hello everyone. Since I have a class for digital logic design coming up, I decided to review by making a small digital project right before the semester starts. I made a small memory game where you have to follow an increasing sequence of button presses until you mess up eventually and have to start all over again. This is a small project that I wanted to explain to my friends in more depth, and hopefully this will improve my ability to explain things to people. I'm hoping this also motivates me to explain my projects rather than just showing what they do here. I intended for this to be a small video for a small project, but while I was cleaning up my circuit, I modified it a lot and made it easier to look at and functionally better. But don't expect it to be the best because I currently have other things that I want to work on, and I didn't fully optimize this project yet. Here is my first finished design. The version used in the showcase might seem a little hard to follow, so I cleaned it up a little. Also, I tried to organize nets so it is clear what is output and what is input. Nets facing to the right are inputs, and nets facing to the left are outputs. Nets facing up or down are comments for a wire, and this might help clarify what a wire does. This input part is different from the previous version because it is safer, but I'll get to that later. Before we get to the physical layout of it, I want to show you the small state diagram I used to design it. This state diagram is not complete, but it was one of the first diagrams I used to design the project. So it shows some of my thought process while trying to make the circuit. Transitions are made when a condition is met. When it is met, it will do an action during a transition, shown to the right of the slash or underneath the slash. The state diagram mainly modifies three main variables. Mem is sort of an array. Each element of this array stores what button number has to be pressed in a sequence of moves. Cur is a pointer to the array used to access memory locations. Top is a pointer to the top of the array, or it can show the number of moves the user has to press. There are 5 states in this machine, and it starts with S1. This flashes the LEDs in the pattern that the user has to follow later. This will be done by accessing memory at every cur, starting from when cur is 0. After that has been played, S1 goes to S2. S2 takes in an input, compares it to memory locations until all memory locations have been compared with the input. If the input doesn't match, then it should transition to S3. S3 resets the memory, turns on the red LEDs, and restarts the game. At S2, if the input sequence matches the correct sequence, the state goes to S4. And at S4, it will add a new move to the sequence and go back to S1. S5 is only triggered from S4 if the high score is beat. S5 lights up green LEDs, plays sounds, and goes back to S1 just like S4 does, but with some extra stuff. Anyways, this whole device is modeled as a state machine with some modified behavior, as some events depend on the current state, and some events depend on the transitions to other states. But it has the layout of a state machine with 5 states represented by flip-flops, with S1 being the reset or initial state, and the net for each state. Transitions to states are shown with nets named 2S number, and they control whether a flip-flop or a state is turned on. And these 2S the two S nets are controlled by this section down here, showing what conditions are needed for these transitions. Two S nets are controlled by multiple S to S nets, showing what states can go to this state. You can think of S to S nets as being the arrows in the state machine. The S to S nets are controlled by a specific condition ended with the state it transitions from. And this specific transition is what you see in the state machine transitional arrows, or the state diagram that was shown before. Sometimes events that are used to control the state are also used to control other things in the machine, such as check next to mem in S2. It's used to increment cur, so that is why it has its own net and is used. There used to be a decoder in the state logic section, but it has been changed for a better design, and we'll get to that later. Mem was implemented using the provided Logisim RAM module. Random numbers are also generated from a provided Logisim module. The 3-bit random number generator always feeds into the memory's input, and memory in RAM will only be accessed by the address cur, and the output will always be enabled. Depending on what state or state transitions there are, a random number will be written to memory at address cur. This only happens at either S4, which adds a new move, or S3 to S1 to make memory at address 0 be random when the game restarts. To implement the values in the state diagram, I made my own basic registers to store and update them. These are important values used for calculation of the next state and also for doing other things. Think of these blocks as flip-flops that can take in vectors or buses instead of just a single wire, and the stuff connected to the input of the flop is the combinational logic used to change it every clock cycle. High score is just the highest score that has been reached by a previous player, and every time that top reaches the high score, this mux lets top overwrite the high score. Cur is an address into memory that is used in multiple states. S1 to light up LEDs corresponding to the data in memory. S2 to compare the user input to the data in memory for all inputs. S3 to set the first memory address to a random value. And S4 to add a new random value to the sequence of moves. This is done by appending a random value to the end of the array. Cur is set to 0 when a state that is not state 1 transitions to state 1. This is so state 1 starts playing the sequence at memory address 0 and can increment cur. S3 is used instead of S3 to S1 because that would cause cur to be set to 0 at the same time memory at cur would be accessed, which causes problems. Over here shows the circuit logic to increment cur. Cur will only increment on states 1 or 2. In state 1, each LED in the sequence will be flashed, and once it is done flashing, cur should be incremented so the next LED in the sequence will be flashed. In state 2, cur is incremented if the input is received, compared, and is equal to the thing in memory. Since the machine stays in state 2 while waiting for an asynchronous input, cur will not be incremented while we are waiting for an input to be received. Top is used to keep track of the number of moves the player has to press. It resets as state 3 and increments as state 4. LED time count is used for the timing of LED flashes, and it will be covered later. These are nets used to calculate the next state or other things, and some of these nets can be seen in the state diagram transitions. This system stops button presses from glitching out. it converts asynchronous input to a synchronous signal. I started this project before I knew how to make a good edge detector with one flip-flop, so I used 2 latches and a bunch of other logic. And this would not be good. This probably would be bad for metastability. Each LED is paired with a button and a number. The button and LED wiring seems unorganized right now, so I cleaned it up. So there are only 2 buttons shown over here. When turned on input LED signal is on, LEDs are controlled by whatever is pointed to by Kerr in memory. The memory value will light up the LED with that same number. And when in S2, which is to get the user input state, the LEDs will not be controlled by whatever Kerr is pointing to, and will be controlled by the buttons. Previously, I used tri-states to control what the input value was, and a press from a button would let a constant corresponding to the button's number go through a tri-state where it would be compared to the memory. The result of this comparison had to be stored in a latch, however, because inval would be in high impedance, and I had overlooked this. I just assumed that it was 0 because the simulator showed it 0. Since it shows 0, it didn't interfere with my design and I just kept adding stuff to it. This had other problems like how 2 simultaneous buttons would cause contention. This could have been avoided if I thought more carefully about tri-states, and I should have known. The second version, however, is much cleaner and doesn't require a latch. It also won't cause contention when multiple buttons are pressed. This version just lets a constant through to be compared to memory using a mux. If multiple buttons are pressed, the result is just OR together. The default value of inval is 0 and stays 0 if no button is pressed. However, this is fine because the comparison's result will only be used after an input button has been pressed. A button can be held down for as long as the user likes, but I need to count a button press only once a clock cycle. If the user holds down for multiple clock cycles, I want the input to be counted once either on initial press or on the release of a button. I made the design so it detects low to high transitions and holds it for a clock cycle to be used by combinational logic somewhere else. This first latch stores if a low signal was detected, then when it goes high, it sets the second latch on, and this second latch shows that a button press has been detected. The first latch then gets turned off and this signal will stay on until there is another clock cycle. The second design is the same as the first, but it detects high to low transitions, and this XOR gate is just used to properly reset the state of the flops. LEDs will light up differently depending on logic, but they will always use LED time count for timing. When the machine is in a state where it needs to light LEDs, LED time count will count from 0 to the 8-bit limit. S3's LEDs will stay lit until this limit is reached, and then it will transition to another state. Input buttons, however, need to turn off before counting to the limit and transitioning to the next state. They are off so that if the same 2 button presses are in the sequence of moves, the player will see the LED flash 2 times instead of it being kept on longer than usual. This pulse is controlled by this value that is plugged into a comparator. When LED time count reaches past this value, the S1 LED will turn off. S5 needs to show multiple LEDs lighting up in order, and that is done using more comparators at different values. If you haven't realized already, the last press of a sequence doesn't show up. It can probably be fixed by using the falling edge detector. This is because it will keep the LED on while holding a button down, instead of detecting it as a press immediately, which will switch out of state 2 and stop the LED. However, this doesn't work here due to other components interfering in my design, and I would probably need to add a flip-flop somewhere to make it work. I don't really want to work on this project anymore, so I've decided to move on and work on different stuff. But anyways, I hope you enjoyed, and see you next time.